Good afternoon, everybody. Till now, we have covered basic electronics and digital circuit framework, and from this class onwards, I'm going to cover the explanation of schematic diagram of laptop motherboard. And as I said in the very first class, I would be taking two as my reference: one the DV2000, another as Lenovo Y570 or Y470, which is an i3 i5 i7 based board. So from this class onwards, we are going to explain the schematics. In today's class, I will cover the V-in detection or DC bat out, and also discuss what is the difference between V-in, what is the difference between V-in and DC bat out. While in some schematic it is written DC bat out, whereas in some schematic it's written V-in. Today in this class, I'll also cover the battery charging section, right? How does the charger communicate with IO controller and the battery, and also some theoretical aspects of ACPI, and I will go into very detail how to understand this entire section of charging, right? So let's start with the class. I'll briefly discuss about all the signals on a laptop motherboard, and I would keep explaining each of the signal whenever it's necessary. So right now I'll just give a brief idea of what signals are present, right? Basically, the entire booting process of a notebook can be divided into two steps, right? One is the hard reset and another is soft reset. By hard reset, you can understand that every component of the notebook motherboard has received power, right? And after receiving power, a PLT reset signal is issued by PCH or by ICH, right? And after issuing PLT reset, the processor gets instructions from BIOS, and all the initialization data would be issued from the BIOS, and this is called soft start. So a notebook start, how does a notebook start? It can be divided into two parts. One is the hard start and another is soft start. Hard start is like entire component of the notebook motherboard receives power, but still it's not working because it's not received logic, it's not received the way it has to operate, and the way it has to operate it can gain from a BIOS, right? BIOS, you can call BIOS as the logic, whereas the hardware, in the first case the hardware gets started, and in the second case logic gets started. So hard reset is like CPU gets its power, right? And the soft start is CPU when it reads from the BIOS and gets the initialization data. That is, we call it as soft start, and it can also be called as a loading of system BIOS and the post power on self test, which is called soft start. So right now, after finishing my the entire concept of hard start, we'll go into soft start. Okay, as I said, a notebook start in two stages. One is hard start and another is soft start. So in the hard start, the entire notebook components get its required voltages, and you can treat notebook as a city where if you do not supply electricity, it won't do anything. It will be cold, it will be dark. Similarly, a notebook motherboard, if you do not provide power to it, it cannot do anything. Like in a city, when there is an overload or there is an underload, there is a fluctuation. You see, when there is an overload, electricity trips down. Similarly, in a notebook motherboard, abnormal voltages can damage components on a notebook motherboard. You will always see in a notebook that voltages at all the points are fixed. They never has to change. The voltages is fixed, and this is, you can call it a law of notebook motherboard. In notebook motherboard, the voltages which are specified on a schematic diagram will never change. And how they get voltages, when they get voltages, this is all about power on sequence, and we call it a power on sequence. So a notebook motherboard, when it traces its entire power on sequences, then the hard start is finished, and after this hard start, the soft start will load on. So what is hard start? As I said, in a notebook motherboard, the voltage has to be fixed at each point which are mentioned in a schematic diagram, and you can treat it as a law of notebook motherboard. If there is any voltage fluctuation, that notebook motherboard will not work properly, right? It won't work properly, and when a component in notebook motherboard will receive voltages, when it will receive power, it's all based on a power on sequence, and we call it as power on timing. So if a notebook motherboard while starting traces its entire power on sequence, then we call it hard start is finished, and after that this soft start will start. We will discuss each of the points very minutely, and if any question arises in your mind, I will always welcome to discuss those points, because I am going to make it as simple as possible. To understand a schematic diagram would be very simple if you have followed my till now classes. Why I have built a base till now is to understand each and every point later on. So now is the right time. We are going to enter the explanation of schematic diagrams, and there we'll follow all the things which we have studied. I will correlate each and everything in my entire class, and in this entire course I'll correlate each and everything. So you have to be thorough with my previous classes. So what I said, in notebook starts in two stages. One is hard start, another is soft start. What is hard start? When the entire component in notebook motherboard receives its required voltages. And I said, in a specific component of notebook motherboard will have a specific voltage, and that has to remain fixed, and you can call it as a law of notebook motherboard or a law of any electronic component, because voltage has to be fixed at a specific point. Current may vary. Current will vary according to the application you are running, right? So if you're running a graphic intensive work on a notebook motherboard, then it will then the CPU will need more current, but the voltages would always be fixed, and that's make the life of a technician very easy, because we have to just check on voltages, right? If the entire notebook motherboard receives its required voltages while starting, then the hard start is finished, and then this soft start will go on. How does this soft start work? What are the various signals in this soft start? We'll be going to unearth those things also, and I think very few have actually mastered those things, how to correlate with BIOS and how to just read the data communication during the SM bus communication or in the LPC communication. For that we do require some specific kind of equipments called logic analyzer, and I'll also show this thing in the today's class when we are going to sniff out the data from the SM bus communication. Okay, so let's go to the next slide. And this is, as I said, I was referring two kind of schematic diagram. One is the Lenovo Y470, and this is Lenovo Y470 block diagram. And we would also be covering one earlier board called DV2000. As I said, many people are familiar with that board, but still there are many questions which people do not understand in a schematic, so I will be discussing those things also. Let's go to the next slide. This is the processor used, and we have the PCH HM65. The Intel HM65 PCH is used on this board. Okay, and now let's start with the starting process. How does the hard start? Basically, what are the sequence in the hard start? Just we'll go briefly and I'll explain each point, each section in detail, right? This is the adapter in and the battery. They enter the charger circuit, and here the charging IC is ISL 88731A. This is, I'm talking about Lenovo Y470. Please open your schematic diagram. Lenovo Y470. This is the input, ADP in and VAT, and you see V in is generated after this section. Whereas in the earlier kind of board you'll find a DC bat out, and we'll see what is the difference between a V in and a DC bat out. Basically, the DC bat out does not require this thing to be passed through the charger IC. I'll discuss this thing in detail. So this is the first step. We have inserted adapter, or we have inserted battery. Then V in is generated, and it goes on to 3.35 volt regulator IC, which is RT8206M, denoted by PU12 on the notebook motherboard of Lenovo Y470. And this regulator, 3.35 volt regulator IC, it generates plus 5V PCU and plus 3V PCU. This is the first step. Kindly note, this is first step. Okay, so we'll go to the next slide, and after generating this plus 5V PCU and plus 3V PCU, it will generate an H power good. A very important thing to note over here is every regulator IC will generate a power good. Every regulator IC will generate a power good, and that power good would get feeded to a next level, which will inform that this IC has worked, has done its job, right? How does a next level? Okay, so just I'll briefly go through the entire steps of the hard reset, and I will explain each steps in detail. And in the today's class we will be just covering this section, the generation of V in, the working of the charger IC, and I will be covering each of this section in the coming classes. So the first step is when you apply an adapter or when you apply a battery, a V in is generated, and it goes to 3.35 volt regulator IC, which generates plus 5V PCU plus 3V PCU. This is the first step. Please note the steps, right? This is the first step, and it generates the power good. I'll just mention briefly over here that all the power good will eventually go to PCH, because PCH and embedded controller, that is the IO controller, they are at the core of power management. So they will eventually go to PCH, but here this is 3.35 volt regulator IC. So this power good will go first to IO controller, right? They'll all bunch together. Every regulator IC will generate a power good, and all those power good will be combined together and to go to IO controller, right? And then IO controller will issue another power good, and it will indicate to PCS that yes, all the power regulators are working. And if IO controller doesn't generate a power good, then the PCH will not work. So this is all done to maintain safety, right? To maintain safety in a notebook. This is a very complex, you can call it a notebook motherboard. It's a very complex, but it's very costly also. So we have to devise a foolproof system. So the manufacturers have devised a foolproof section, and all the voltage regulators will generate a power good, and this power good will go to IO controller except the CPU voltage regulator, which will directly generate a power good, and it won't go to IO controller, right? It won't go to IO controller. We'll see all these steps over here. So in the first step, it generates the 3.35 volt regulator IC. Here this IC is RT8206M and indicated by PU12, which you can also see on that notebook motherboard. And please open your schematic when I'm explaining each and everything. The RT8206M is 3.35 volt regulator IC. In the first step, it generates plus 5 VPCU plus 3 VPCU, and it generates a power good, H power good, right? Generates power good, that means it indicates to the next system. Here in the here this power good is going to IO controller, so it indicates to the IO controller that yes, this voltage that I'm working okay, I'm working fine, right? So let's go to the next slide. And after getting plus 3 PCU, it goes to IO controller, right? And this acts as a, this is going to a register R304, and the plus 3 VPCU is directly going to EC also as a power supply, right? So, and there's a clock, there is a clock, embedded clock in this IO controller IT8518. So as I said in my previous class of digital circuit framework, any IC, integrated circuit, it requires three things. One is the supply, reset, and clock. Here this plus 3 VPCU is acting as a supply, and plus 3 VPCU here is acting as a reset, and the clock is embedded. So now this IO controller can work, but not all the parts can work. Only the power management section of this device can work, right? Not all the sections. So the second step is getting over here, reset, supply has already come to IO controller. So in the third step, it will generate S5 on, and this, in the third step, this S5 on is going to a MOSFET. Here I have indicated it by SW because MOSFET generally acts as a switch in a notebook motherboard. So it goes to the gate of this MOSFET, and it will generate plus 5 underscore S5 from plus 5 PCU. This has already been generated as I seen in the previous slide. Similarly, this has already been generated, and it generates plus 3B underscore S5. We'll discuss about these things, what is S5, S4, S0. This is all about ACPI. Before going into that detail, I give a lecture, a theoretical lecture on what exactly is an ACPI, what it has been implemented, and how helpful it is. So in this class, we'll just move slowly and slowly, understanding each part. Just let us notice about the various signals going over here. Okay, so this 3V underscore S5 goes to the RTC section of the PCH, right? So here we have already covered the 3 and 4. So at the fourth step, the PCH RTC section has received power. I'll also discuss about this RTC section. People always get confused with this RTC section. What exactly is RTC section? Whether this RTC is actually in the battery? Sometimes somebody asks me, so why does it require battery? We'll discuss all these questions and how important is an RTC section. If it doesn't work, your notebook mother won't work. So this is the heart. This is the heart of hard reset. You can call it as a heart of hard reset because this is the starting point, right? This is a starting point of powering on notebook motherboard. So this is the fourth step, and in the fifth step, when we press the power button, this is switch. When we press the power button, it will generate an NBS on, right? Or some in some schematic you'll also find some different name. The power button signal is there. Fifth step, this is the fifth step, and after receiving this NBS on signal, the EC, the embedded controller inside this IO controller, will generate a signal RSM reset. What is exactly the full form of RSM reset is resume will reset, and I will go into details when I will be covering the IO controller. So this is the sixth. After getting RSM reset, the PCH will after getting RSM reset, and another signal is generated, SIU underscore power button. After getting this two signal, the PCH will generate two more signals to IO controller. PM underscore SLP underscore S4 and SIO underscore SLP underscore S3. What exactly these two signals are? These are an indication to the IO controller to start the S4 stage, to start the S3 stage, and there are several kind of stages in the power sequence, and we'll discuss all these stages in detail, right? No shortcuts, we'll be discussing everything in detail. So I'm just crossing this in today's class so as to get into our main class, and into today's class I will be discussing about the generation of V in and all about charging, right? All about charging. So this is the 9th A, and after getting this two signal, the PM underscore SLPS4 and SI underscore SLPS3, the EC will generate a sus on. This is the 9th A, sus on to RT8207L denoted by PU9, and it will generate 1.5 volt underscore sus, 1.5 volt underscore sus. And again this is a voltage regulator, so it will generate a power good, H power good. So this is the 9A step, and this is 10A step. Let's go to the next slide. And EC will again generate a main on signal. It will go to all this regulator OZ8117L, 17L, all this PU7, PU8, PU6, PU10, PU5 to generate various kind, to open all kind of voltages, right? After getting main on signal, 1.05 volt underscore PCH is generated, it will generate H power good. It is generating 0.85 volt, it is generating 1.8 volt, and it's generated this is the voltage for the graphic section, right? And this is generating the 1.1 V underscore GPU. So after getting the S4 and S3 signals, the embedded controller will issue two kind of signal. First the sus on, and then main on, and the all kind of voltages are then getting opened up, and all the power good main on, and the main on is similarly going to other section as well to generate to the MOSFET SW. Here the SW is basically for MOSFETs. It's going to these MOSFETs to create plus 5 volt from plus 5V PCU, to create plus 3V volt from plus 3V CPU, to create plus 1.5, this is a run voltage, right? Main voltage from 1.5 sus, and similarly all kind of stages are there. We'll explain all these stages. I'm covering this fast because I'll just give an idea. I'm just giving an idea how this power sequences are, how how in the notebook motherboard various power are getting opened, right? In a stages. They're not getting open instantly. They're getting open in stages. And here you see all the power good generated by the regulators, all the power good generated by the various regulators are combined together to issue a H power good, and we call it all power good, and this all power good is going to embedded controller. And after a delay of 99 millisecond, this IO controller, after getting this H power good, first it will generate VRON, and after generating VRON there would be a gap of 99 millisecond, and it will generate EC power. Okay, this VRON is going to the CPU core regulator, and it will generate the VCC core, and after getting this VCC core, generating VCC core, this core regulator will generate the CPU core voltages. Okay, so all the regulators have generated their power good, and all the power good is combined together to offer a power good to the IO controller. So that was the step number 12. And after the EC, the embedded controller inside this IO, that is IT8518, receives power good, it will generate a VRON, that means voltage regulator on, and this signal will go to the CPU core regulator, and it will generate VCC core, and at the same time you see VCC core, at the same time the IO controller will generate EC power, okay, and there is a delay of 99 millisecond between this power good and this EC power, okay. So you can see everything on a notebook motherboard is very much fixed, right? It's a very much timely fixed. There is a time to everything. So if there is a more delay, then if there is a less delay, then this entire system will not work. You can see EC power okay and VCC core, they are generated at the same time. You can see both of them are labeled as step number 14. So a time factor, this time factor is very important, and we will discuss this delay of 99 millisecond. Why 99 millisecond is there? Why not complete one? Why not 50 millisecond? There's a very important concept behind it. So after a delay of 99 millisecond, this IO controller will generate EC power okay. At the very same time, the voltage regulator, the CPU core voltage regulator have generated a VCC core, and the step number 15, it will generate the voltage regulators will generate IMVP power good, and it's going to a AND gate, and this EC power okay is also going over here as an AND gate, and this EC power okay, it's been divided into two portions. One is going to power okay, pin of the PCH, and another is going to AP power okay. What is the difference between both of them? We'll also discuss this in PCS section. For timing, AP power okay means active sleep power well okay. This seems to be very complex, but when I will be discussing the PCH or the complete ACPI, I will be explaining each and everything. So here a very important concept is there is a delay of 99 millisecond, okay. So this IMVP power good and EC power okay, both are ANDed together. Why AND gate is there? Why not a OR gate? AND gate is there in order to check that both of the signals are present. If you have an OR gate, then if anyone is present, then it will give output. But AND gate is here to check the presence of both of these signals. Both of these signals means this is also okay and this is also okay. So at every point in notebook manufacturer, the manufacturers have devised a way to check the preceding devices. These are preceding devices, right? In order to operate the PCH completely, it is checking at each point whether all my regulators are okay, whether IO controller is okay. So both of them are ANDed together, and it's going to sys power okay, and this sys power okay wire resistor is also going to the 1.5 voltage regulator to generate an LDO voltage of 0.75. This is very important. You can see the 1.5 underscore sus is generated in 10A, whereas the same voltage, the LDO voltage, is generated after around 7 steps after, and this is the termination voltage. We'll also see the generation of the termination voltage is quite different in a dual core board and in i3 board. Both of them are very different, and we will be discussing when I'm going to explain both of them, both of this circuit. Okay, I'll also explain how the termination voltage generated in a dual core based board and how a termination voltage generated in i3 board. You can see very much clearly the 1.5V underscore sus is generated in the 10th A step, whereas the 0.75 volt termination voltage is generated at the 17A. So these are all power sequences. Just I'm going through it fastly right now in order to give you a view how a notebook motherboard get us started on, how the hard start of notebook motherboard operates, right? So after this step, after the 16th number step, the 17th number step is the PCH generate PM DRAM power good, then it generate CLK underscore CPU underscore BCLK, and I will discuss this signal was actually being generated by a clock generator in a dual core baseboard, but here it's generated by PCH because a clock generator is inside this PCH. And there is a very important, how does this clock generator inside PCH operates? Where does it get inputs from? There is a management engine BIOS, ME BIOS in SPI BIOS. This management engine BIOS, it's the job of the management engine BIOS to initialize these clock generators. And I'll discuss this ME BIOS inside the SPI BIOS, which is very important. So this is CPU BCLK positive, and this is CLK CPU BCLK negative, and this is H power good. So the CPU gets H power good, and after this the PCH generates PLT reset, which is almost the final step. The CPU needs reset, and this is the final step of the hard reset. So I think we get an idea how a notebook hard start operates, right? Hard start operates. At some of the point I have told hard reset. It's not hard reset, it's hard start. Hard start, soft start. So what is the final point of hard start? The final point of hard start is CPU underscore PLT reset. That is, the processor gets its reset. And what is the start? Start is when V in or DC bat out. That is the start of hard start. Okay, now we'll go into details and study each of these steps properly in great detail. Okay, so now we have covered a brief overview of the hard reset of a notebook motherboard, and now we'll be covering each things in great details. So let's start with a adapter is inserted in a notebook motherboard over here at the DC jack, as you see over here, at a DC in at the DC jack. So if adapter is connected over here, then a current will flow across this section. And please open your schematic diagram of Lenovo Y470 and Lenovo Y570, the adapter section, and there you can find out these things. So the adapter is inserted over here, it will drive a current across it, and this VA is generated. VA, that is voltage ampere, and VA1, it generate VA and VA1. Now this is a P channel MOSFET. How I know that this is a P channel MOSFET? As I have explained, a MOSFET in which the arrow is outside is a P channel. But normally in a P channel MOSFET, we observe a current flows from source to drain, right? Not from drain to source, but source to drain, right? But here the input is connected to drain and the output is connected to source. So in this case, and the gate is grounded. So in this case, this MOSFET, the diode inside this MOSFET will act as a damper diode, and this MOSFET will basically act as a diode, and the current will just pass across this MOSFET. As I have explained in my MOSFET chapter, that we can replace this MOSFET. The question arises, can't we replace this MOSFET by a diode? No, we can't replace a diode in case of MOSFET, because across a diode you have a voltage drop of 0.5 to 0.6 volt, but across a MOSFET there is no voltage drop. The voltage drop is negligible. So, and we cannot afford to have any reduction in voltages in a notebook motherboard. This is, you can call it as a law of notebook motherboard. So we have put a MOSFET over here, and there is a very interesting feature over here also. There is a very interesting feature also, that this MOSFET can be used to block the flow of current in the reverse side by applying some voltages at the gate. We'll study basically in the next phase. So here we have connected the adapter, it will drive a current, and the current will go across this MOSFET, treating it as a diode. Okay, so it will generate 19 volt. This 19 volt from here, this 19 volt has reached here and here. That means these two wires can be treated as sorted, both of them having same voltage, right? This and this. So, and we'll go to the next slide. Okay, and this VA is going to the charger IC, the ISL 88731, and we'll discuss the data sheet of a charger IC. In a data sheet of charger IC, there are two important things, two important inputs to a charger IC. One is DC in, okay, and after getting DC in, this ISL 88731 will generate an LDO, okay. So this LDO, okay, and this LDO has come across this VDDP pin, and this LDO has actually lot of function to drive this charger IC internally. This LDO is very important. When we discuss the data sheet in this class of the charger IC, we'll notice how important this LDO is. So the VA has come at DC in, it will generate a LDO at VDDP pin, and the next step is the VA is going across the AC in also through a resistance divider. Okay, there is a resistance divider and it's going to the AC in. So the charger IC has got AC in, DC in, and if it gets AC in, the charger IC will output AC. Okay, basically the charger IC delivers two type of output. One is analog output and one is digital output to indicate to IO controller that the AC adapter is present. How does a IO controller know that the AC adapter is present? The charger IC will output a AC OK signal, right? And it also output a input current sense, right? Input current sense output, how much this charger IC is getting input current. It will also deliver an analog output to the IO controller, and you will notice in the data set how important these signals are. So the VA is going to the DC in and to the AC in. And DC, after getting DC in, it generates LDO. Kindly note the sequence. Let's go back. Okay, so this VA is coming to the charger IC and it will generate an LDO at VDDP pin, and again this VA is going to the AC in, and this will generate an AC OK signal which ultimately becomes AC in, and this AC in signal is going to the IO controller, which indicates, it's a kind of digital output which indicates to IO controller that yes, AC adapter is present. Okay, and now this AC OK signal, you can notice over here, this AC OK signal is going to a transistor and another to a P-channel MOSFET, right? P-channel MOSFET, and this AC OK, the AC OK generated, let's go back to the next slide. Okay, this AC OK generated over here. This AC OK will go to this section and it will turn this MOSFET on, because this is an N-channel MOSFET. You can please go to the schematic diagram, see the schematic diagram, and in the schematic diagram you can notice this AC OK is coming over here. This is N-channel MOSFET because the arrow is inside. So for an N-channel MOSFET to conduct current, the VGS has to be positive, so the gate is at higher voltage than source, so it will allow current to flow from drain to source. That means the switch will get closed. So go back to the presentation and we'll see over here. Yeah, so this will conduct ground, right? And if it's conduct ground, then this will provide a path, right? This will provide a path to go over here, because ground has shifted now over here, because if it's conduct current, this will be at ground, so this point will also be ground, this point will also be ground, so it will give a path to flow from here, right? It will give a path, right? Here it's a transistor, all right? In a transistor, if VBE, if voltage at emitter is greater than voltage at base by 0.6 or 0.7 volt, then the transistor is in saturation mode. So this transistor will conduct current, and here you can see this is at 0 number. This has reached at 0 potential, so it will provide a path, right? It will provide a path to flow current. So here some current will be there at the base, right? And you can see some current will be there at base. There is a resistance, so this 19 volt will fall down to 6 volt, and the 6 volt is present at the gate. Now you notice over here, this is a P channel MOSFET, right? For a P channel MOSFET to operate, we know VGS has to be negative. So the voltage at gate is 6 volt and the voltage at the source is 19 volt. So in case VGS is negative, that means this P channel MOSFET will now turn on, right? So this will turn on and the current will flow across this. Let's revise once again. This ACOK is going over here. This is N channel MOSFET. In N channel MOSFET, we know VGS has to be positive. That is, voltage at the gate has to be greater than voltage at the source. So VGS is positive over here because ACOK is approximately around 3.3 volt. So this will turn on. So the ground would shift over here. So the current would like to flow across this, and this transistor will be in saturation mode because VBE is greater than 0.6 to 0.7 volt. Voltage at emitter is greater than voltage at base by this volt. So it will conduct a current. Some current will flow across this, and so voltage would get dropped. This Vin would get dropped across this resistance, and 0.6 volt is present. 6 volt is present over here. Now this is a P channel MOSFET. For a P channel MOSFET, VGS has to be negative. So voltage at gate is 6 volt, and voltage at source is 19 volt. So this is negative. So this MOSFET will turn on, and this Vin is reached over here. But this MOSFET has to close down because this MOSFET is connected to the battery, right? So it has to close down. You can see over here the collector, the current going to the collector will go to this, and this is a P channel MOSFET, right? And in the P channel MOSFET, this current will be this voltage would be more or less than VA1. So this VA1 is going over here, and this Vin is more or less than VA1. So the VGS is close to 0. So VGS is close to 0. So this MOSFET will turn off because this is a P channel MOSFET. We know in a P channel MOSFET the VGS has to be negative, but here at the gate this voltage is coming. The VA1, close to VA1 is coming. There is a close to 0 voltage difference between gate and source. So VGS is close to 0. It's not negative. So this MOSFET will turn off, right? And it has generated a Vin. We'll notice this in schematic diagram. We'll go to the schematic diagram. Yeah, in the schematic diagram, as we told, VA1 is generated over here. This is a P channel MOSFET, but we know in a P channel MOSFET, if the input is connected to the source, then in that case VGS has to be negative, but here the input is connected to the drain, so it will act as a diode, right? It will act as a diode, so current will flow across this. VA1 is generated over here. This IC, this charger IC, the DC in, VA is going to the DC in, it will generate an LDO voltage, so it will come across this VDDP P, and AC in the same VA through a resistance divider is going to AC in. So this charger IC will give a digital output of AC underscore OK, and it will go to create an AC in signal. and that will go to the IO controller, right? That will go to the IO controller. Now this ACOK will also make this transistor to make this MOSFET to conduct. So if this AC on is coming over here, this is conducting, so the ground will shift over here, right? The ground will shift over here, so this transistor will the current will flow across this transistor. It will become in an active mode, and this it will flow, the current will flow across this resistance. So the voltage across would be approximately 6 volt. This is a P channel MOSFET. For a P channel MOSFET to operate, we know VGS has to be negative. Here at voltage at source is 19 volt, voltage at gate is 6 volt, so VGS is negative, so it will turn on and it will generate V in. But this MOSFET has to turn off, right? Because we have inserted an adapter, so this is battery connector, so it has to get turned off, and it will get turned off because this VA1 is now present over here, and at the source V in, which is close to VA1, is present over here. So VGS is close to 0, so this will turn off, because in P channel MOSFET VGS has to be less than 0. So this switch will turn off, and the battery is no more connected over here. So V in is basically, if battery is present, then this battery volt will in, if battery is present and AC adapter is not present, then this battery voltage will come across this V in, and if AC adapter is present, then AC adapter voltage is present across this V in. And in i3 board it is called V in, whereas in dual core board it's called DC bat out, and we'll check the DC. This is DV 2000 board, and we'll look to the adapter section. Let's check this, the adapter section of DV2000, and we'll correlate things, right? Always we need to correlate things. This is, suppose the adapter is connected over here. Now this is 4407. This is a P channel MOSFET, right? For a P channel MOSFET, we know the current will flow from source to drain if VGS is negative, right? Here the gate is connected to the ground, source is at higher voltage, so VGS is negative, so this switch will turn on, and this voltage will appear across this AD plus, right? This voltage will appear across this AD plus. Now let's see the charger IC. Let's see the charger IC section, and we'll move to the charger IC section. We'll find out which one is the charger IC over here in this DV2000 board. And yes, this is charger IC is 8725. So we'll search max 8725, and we'll find where it is, max 8725, yeah, and we find it over here. So the AD plus is going over here, right? Similar in i3 board, we have over here, you can check, this is AC in is connected, sorry, the DC in is connected to VA, right? VA. Here in DV2000 board, this AD plus is coming over here. So DC in and AC in through a resistance divider, this AC in is coming over here, right? And it will generate ACOK. But you will find over here, there's no ACOK is not going anywhere to open a MOSFET, right? Here in this case, you will see over here the ACOK is basically going to open a MOSFET so that the VA become V in. But here in this DV2000 board, you can see this AD plus, and you can see this is an N channel MOSFET. You can see this is N channel MOSFET, right? So for going to flow across this, you can see this is N channel MOSFET. Are you sure this is N channel MOSFET? No. 4407. This is a P channel MOSFET. The arrow is outside, so this is P channel. And we know in a P channel MOSFET, the current will conduct from source to drain only when source is connected to the input side. Here the input is connected to drain, so it will act like a diode. So this AD plus will come across this point, right? It will become AD sys, and this AD sys is becoming DC bat out, right? This is becoming DC bat out. There is a, but if the adapter is present, then this charger IC will turn off this MOSFET from here, from PDL signal, right? From PDL signal. When the adapter is present, this will turn off. When battery is present, this will turn off from PDS signal. Here it's a more protection. The DC bat out is no more controlled. The DC bat out is no more controlled by the charger IC. You can see it's no more controlled by charger IC in a DV2000 schematic. The DC bat out is there. Here AD plus is coming over here. It has no effect of this charger IC. If this charger IC is not okay, even though DC bat out will come over here, right? Whereas in i3 Lenovo board, this V in will generate only when this will AC OK will come. When adapter is present, this V in will generate only when AC OK is present. It's not going to any MOSFET to open it up, right? Whereas in DV2000, this opening, when adapter is present, DC bat out will get generated. This will turn off through this PDL switch, and we'll discuss the schematic, the data sheet of this charger IC in great detail in this class only. Okay, so till now I think we are okay with all the things that I've explained. I'll go once again. This is the first point. Adapter is connected over here. This is going across this. This is a P channel MOSFET. As I said in a P channel MOSFET, current generally flows from source to drain only when the input is connected to the source. But here the input is connected to the drain, and the gate will have no effect, so it will be treated like a diode, and this current will flow across this, and VA1 is generated, right? This VA1 is going to the DC in, and after getting the DC in, the charger IC will generate an LDO voltages, right? VDD pin, and this AC in is coming, and this charger IC will generate a digital output AC, okay, which will become an AC in, and it will go to the IO controller, right? This signal will go to the IO controller to indicate the presence of adapter. And in this class we'll also be going to study the smart battery, smart adapter section. Here I'm just explaining you the schematic, but in this class only we are going to study the entire system: charger, IO controller, SM bus, battery, where does they fit, right? Where does they fit? So this charger IC will generate AC OK signal, and this AC OK will go to open up this MOSFET. It will go to conduct this MOSFET, and after conducting this MOSFET, the ground will shift over here, so it will conduct current, right? It will conduct current, so a less voltage will be present at the gate, and VGS is negative. This is a P channel MOSFET, that was the N channel MOSFET, so it gets connected and VIN is generated, but we have to turn this MOSFET off. So for turning this MOSFET off, the current is going over here, right? The current is going over here. The voltage at gate is more or less equal to voltage at source, so this will get turned off. This is the way of generating V in a i3 board or in a Lenovo board, whereas in a dual core board, we see in a dual core board, this is a P channel MOSFET, so it will treat it like a diode. This adapter volt will come across this, and it will be treated as DC bat out. And when adapter is present, this MOSFET will get turned off from this PDL signal, right? PDL and PDS is very important, and we'll look into detail after we study the data set of this. Okay, so let's go to study the smart battery, smart adapter section, and then we'll come back at studying the data set of this both of this charger IC. Okay, so till now we have discussed about the generation of V in and DC bat out generation, right? V in and DC bat out. DC bat out was generated in a DV2000 board, whereas V in generated in Lenovo board. Because in the very first class I have told that I will be discussing two schematic diagram, and when we understand this two schematic diagram, we can understand any schematic diagram. Alright, so we have discussed here the generation of DC bat out and wheel till now. Before going to explain the data sheet of charger IC, I would first like to refer this United States patent document which are taken from Google about the smart battery charger system. One very important point I like to mention over here is a notebook battery is very much different than a normal battery. You can call like a normal battery present in a torch. Those are very much different than a notebook battery. We call notebook battery as a smart battery. Why smart? Because that battery can transfer certain information about its charging voltages and charging current to the charger IC. Whereas if you talk about other battery, they don't have such mechanism to transfer such data. So the transferring data, so the mechanism of transferring data, and that to updating, right? Updating with activity. Like if the notebook motherboard is running graphic intensive work, then in that case the heat generated in the notebook motherboard would be more. Then the battery will send information to the charger that it require a larger charging voltage, because we'll talk why a larger charging voltage is required when a temperature increases in a notebook motherboard. So understanding this smart battery charger system is very important. What exactly is in a smart battery charger system is, in a smart battery charger system, it includes smart battery and smart charger, right? Smart battery and a smart charger. Now let's look what is inside a smart battery. Inside a smart battery, you see this is VBAT, that is the battery voltages, and this is positive and negative. It's getting connected to the rechargeable battery which supplies the voltage actually, right? And there is a data and clock pin, and inside this battery you will find a microcontroller. This microcontroller makes battery smart, because this microcontroller stores information, process information like capacity alarm value, runtime alarm system, present runtime value. What exactly this present runtime value indicates? Present runtime value indicates to the system. It will transfer this information via SM bus. This is connected to the SM bus. This SM bus is connected to the IO controller. So it will transfer this information, the present runtime value. That means how much this battery can support. 1 hour, 1.5 hour, 2 hour, how much hour it can support. It will transfer this information via SM bus to the IO controller. The IO controller will then transfer this information to the CPU, and the operating system will retrieve this information from the driver, right? From the ACPI driver, and it will indicate in the taskbar. It will indicate in the taskbar that this much hour is present, this much hour this battery can support. And this microcontroller makes this battery smart. So you get the difference between a normal battery and a smart battery. In a smart battery, it can transfer its information, how much this battery can support. It can also indicate to the system, no, I am getting to the trip point, my value is getting low. So you'll get indication on your notebook that this battery is now going to die, right? So this information is processed by a microcontroller inside this battery, and that makes this battery a smart battery. And let's see this graph. This graph is a very important feature. By this graph you see, as the temperature increases, the self-discharge increases. You see, the self-discharge increases. So it is advisable to store notebook battery at cool places, because if you store battery at not so cool places, then the self-discharge will increase with temperature, and it may happen that the battery cell will self-discharge to 0 volt. And I have seen these cases happening with basically with importers or wholesalers of laptop batteries, because they import batteries in a big quantity and store the battery, but if those battery are not sold, if those battery are not getting used up, then those battery are self-discharging. And I think many people have contacted us for the solution to this case. There is solution to this case, but there is solution to this case only when the rechargeable battery present inside the battery has not reached its zero value. If it's not reached its 0 value, we can boost it. We can boost this battery to its initial value. And there are certain devices used to boost this value. I'll go into these things, something which are apart from repairing. I'll take these classes at the end of the course. Okay, at the end of the course, how to use certain tools like laptop battery tester, logic analyzer, how we can remanufacture a battery. I'm going to discuss these things also, but I'm not going into details about how to remanufacture a battery, because these are all patented information, right? These are all patented information, but I'll discuss a layout that how can we remanufacture a battery. Okay, so I was discussing about this smart battery. So this microcontroller inside this battery makes it smart. Okay, and with this graph it shows that when notebook temperature increases, how does a notebook temperature increase? It may run graphic intensive work. In that case, lots of heat would be generated by the CPU, and in that case the self-discharge of the internal battery may increase. So this battery will need more charge voltages, and how would it transmit to the charger that I would require more charge voltages? It will tell this microcontroller will send information via this SM bus. Okay, so that's why I referred this graph. And let's go to the block diagram, and this is SM bus, right? This is SM bus. SM bus is a system management bus, and this is quite similar to the I2C bus technology developed by Philips. And in this case, this is basically a two-wire connection, one for clock and one for data. If you like, I would go having a separate class of SM bus later on, but right now you should understand SM bus to be a two-wire topology, where in this SM bus system, the system host can be anything, but when you are referring to a notebook motherboard, the system host is IO controller. This smart battery charger is the charger IC. In case of DV2000, it's MAX 8725 here. Okay, and in case of the Lenovo board, this is ISL 88731 is the charger IC. Okay, and this is the smart battery as we have spoken of. And let's go to the main block diagram. So here you can see smart battery charger, smart battery, and system host. They're all communicating with each other, right? If a smart battery the value or the capacity of the smart battery has reached its critical point, then it will generate a critical event signal to the IO controller through SM bus, right? Through SM bus. Here we'll come again. and see, because these are very important concept and we must understand these things very smoothly. And if you feel any problems, you should just email me up. Okay, this is SM bus, data and clock. So you can see how they are communicating with each other. And a question arises, can we sniff this communication? Yes, we can sniff this communication, but it requires some tedious methods, and we'll discuss it in the last phase of the today's class. How can we sniff this data communication? Okay, so smart battery chargers, smart battery and system host, they're all communicating through a SM bus. So I hope the smart SM bus technology and the smart battery charger system is clear to you. And now we'll discuss the pin details of the charger IC MAX 8725 and ISL 88731A, and we'll differentiate between these two charger IC, how they work similarly and how they work differently. Okay, so let's go to discuss the data sheet. Okay, so till now we have covered the smart battery charger system, and now we'll cover the entire charger IC. We'll try to understand this charger IC in a greater detail, and so I have taken up the data sheet. You can understand any electronic IC if you understand its data sheet, because inside the data sheet all the valuable information are written about that charger IC. So I have opened the data sheet of Maxim 8725, which is a charger IC present inside the DV2000 board, and I will correlate this data sheet with the actual implementation on the notebook motherboard. So we'll try to study what exactly this MAX 8725 is. It's written MAX 1909 and 8725, so both of them are same, except there is one more feature in 1909. There is a reconditioning feature. There is a conditioning charge feature in MAX 1909 which is not present in 8725, but they can be replaced, right? You can replace a MAX 8725 by a MAX 1909, but you cannot replace a MAX 1909 by MAX 8725, because in that case you will lose the capability of reconditioning the battery. Reconditioning is like when adapter is also present and battery is also present, then in that case the reconditioning means the battery would get completely discharged and it will again charge through the adapter, and that feature is not present in 8725. So let's study this data sheet, and it's written the maximum current drawn from AC adapter is programmable to avoid overloading the AC adapter when supplying the load and battery charge simultaneously. So we'll understand what is the meaning of this line is. It says that this charger IC, the maximum current drawn from the AC adapter is programmable. It's programmable. This input, this maximum current drawn value, maximum current drawn by the charger, the output is given to the IO controller. We'll see in this data sheet. And the MAX 1909-8725 provides a digital output that indicates the presence of AC adapter and an analog output. The digital output is AC OK, whereas the analog output is, we'll see the analog output, and that is IINP, right? Input current monitor output, and we'll see in this data sheet. So let's go back direct to the pin details, because we have to understand the pin. And at page number 13 we find the pin DC in. This pin is DC supply voltage input. Let us see it in its actual implementation. So the DC in, right? Where is the DC in? Yes, DC in. The adapter voltage is connected to the DC in, right? So let's go back again. And LDO. LDO is device power supply. These are the pin details, but we'll also go to see how does they are connected internally, and that is in page number 18, I guess. And let's know, not here, but understanding this data set is very important. Yes, over here you see DC in and LDO. You see DC in is connected to an internal 5.4 volt linear regulator, and that would generate an LDO, and that would generate an REF. So when DC in is connected over here, after getting the DC in, the charger IC will generate an LDO, low dropout, and the value at this low dropout would be 5.4 volt. There is an internal linear regulator present over here. Okay, go back to page number 13, and LDO AC in. AC in is AC detect input. Okay, you can see over here it can be used to detect the presence of charger power source. The comparator open drain output is AC OK signal. Let's go back to 16 page number, and AC in. We'll see where, yes, AC in. You see AC OK and AC in. There is an internal comparator inside this charger IC, right? Internal comparator, as we have studied in digital circuit framework. What does a comparator do? A comparator will generate here high value if this AC in is less than 2.048 volt, and in that case if it's get high voltage, then AC OK would be 0, right? AC OK would be 0. That is, if there is no adapter present, if the adapter is not present, then this value would be 0, and in that case it would provide a high value, and in that case it would get grounded. So AC OK would be 0 in that case. But if AC in is present, that is adapter is present, then this will provide a low value. Low value means the gate voltage would be not connected, and in that case this AC OK would be high value. And you can see the actual implementation over here. You see AC in, AC OK, and AC OK you see is tied up to externally by max1909 underscore LDO, and through a resistor. This value is 5.4 volt as seen over here. This is 5.4 volt. Okay, so if AC in is present, if adapter is present, then this would be given less value, that is this is not connected. In that case AC OK is connected to LDO. Okay, AC OK is connected over here, max 190 underscore LDO. This value is 5.4 volt. There are two resistors across this, so there would be some voltage drop, and this would be approximately around 3.3 volt. And if adapter is not present, then what would be scenario? If adapter is not present, AC in is not present, then this comparator, this is 0, so this will give you high value. That means this MOSFET will turn on and this switch will close, and this AC OK would be 0. So if AC OK is high like 3.3 volt, that indicates the presence of AC adapter. So it's a very good comparator inside this charger IC. Okay, so we'll understand each thing slowly. Okay, yeah, let's go to page number 13. Reference. Okay, we'll again go over here. What is reference? Reference is basically reference for the charger IC. We'll go over here, 16 number reference, 4.223V volt. This is generated by internal linear regulator. And we'll go inside again to page number 13. Ground, this is ground. PK press. Where is PK press? What exactly PK press means? PK press is if you pull PK press high, it will disable charging. You see there is a bar over here. Any bar on any signal will indicate that this will become active when it is having low value, and it will not be active when a high value is there, right? So it's written pull PK press high to disable charging, and this PK press signal is coming from, of course, battery. We'll see over here. 16. PK press, yes, this PK press, and it is going to the charge logic. So if we put it high, then this charger will disable charging, because this is the charge logic. It will disable the charge logic, and you see this charge logic is connected to the internal DC-DC converter, okay, and that DC-DC converter generates DHI and DLO, which is connected to the gate of the MOSFET. You can see over here, PK press BT underscore TH, and it's coming through the battery, BT underscore TH coming through the battery, okay. So if we pull it high, then it will disable the internal charging section. You see again over here, it will disable the internal charging logic, and if it will disable the internal charging logic, the internal DC to DC converter will not work, and in that case DHI and DLO will not come. And you can see where DHI is connected, DHI, drive high, and this is connected to the gate of the top MOSFET, and DLO, this is connected to the gate of bottom MOSFET. So if the battery pull it PK press high, and why, and when it presses PK press high, when temperature is high, okay, when battery is fully charged, then it will disable charging by pulling PK press high, and in that case it will disable the charge logic. And if charge logic is disabled, then the internal DC to DC converter is disabled. It's connected to the DC to DC converter, then DHI won't be generated, DLO won't be generated, and so the top gate MOSFET and the bottom gate MOSFET will not operate, and so charging voltage will not come. Okay, till now I'm clear? You have to see the internal structure of the charger IC to understand each and everything. Okay, so we have discussed DC in, it generates LDO. When DC in comes, it generates LDO. AC in, AC OK. If AC in is coming, AC OK is coming. Okay, and we have studied PK press, what PK press is. We'll go back to page number 13. AC OK we have understood. IINP, mode, it determines the mode, right? Mode means it will generate, it will basically setting for the number of cells and asserting the conditioning mode. Will not go into this detail. Basically it would be used in 1909, max 1909. Okay, IINP, what is IINP is, right? What is IINP is? This IINP, it gives information to the IO controller how much charger IC is sensing input current, how much charger IC is sensing input current, and it is basically dependent on CSSP and CSSN. Let's check over here. CSSP is connected to the positive side of the adapter supply, and CSSN is connected to the negative side of the register. Okay, so CSSP and CSSN, how does it generates IINP? We'll have to look over here also. We'll go to page number 16 to understand the internal, and you see CSSP and CSSN is connected to a op-amp. Okay, it's connected to an op-amp, and this op-amp is generating an output, and this is going to another op-amp, and it's generating IINP. And we'll see in the schematic where does this IINP is going. You see IINP, this is going to IINP is going over here to generate AD_IA, that is detect adapter input current. This is an output of this charger IC to the IO, and we can see over here to the charger IC. You can see over here, see IINP, see over here, this is input to the IO and output from the charger IC. Okay, and ACOK is another output of the charger IC and an input to IO. So ACOK and IINP. ACOK is digital output and IINP is an analog output. ACOK detects the presence of AC adapter, while IINP gives you the value of input current sensed to the IO controller. Okay, we'll go back to page number 13. Sorry, and we'll go to the page number 13. So IINP, we have understood what IINP is. ICTL and VCTL, these are, I'm just discussing the important pins. What we have to look those important pins, right? We have to not be concerned with all the pins. I'm just discussing the important pins. So we have to be clear about ICTL and VCTL. ICTL is input for setting the maximum output current and input for setting the maximum output voltages. We'll go by here, ICTL and VCTL. You see over here, ICTL is an output from the IO controller. This is basically an IO controller, is an output from the IO controller to basically determine the maximum output current. This current, maximum output current. Okay, ICTL and VCTL. We can check in a schematic. Let's check in a schematic where ICTL is. ICTL max 1909 ICTL, and this ICTL you see over here, max 1909 ICTL, and this charger on signal is coming from the IO controller, and that is determining the 1909 ICTL, and basically it does this increase or decrease the value of current through operating these MOSFETs. Okay, so ICTL is an input from the IO controller and VCTL is for input for setting the maximum output voltages. Okay, we'll go again to page number 13 and 13 and ICTL, VCTL. This is battery voltage feedback input. Let us go to page number 16 first. BAT, and you see over the BAT pins. We have to see, or we can see, you can see BAT pins. This is a direct connection from the battery to the charger IC, and we can see in a schematic also. This is BAT BT plus sense coming from the battery terminal. Okay, so basically it is for sensing the battery, right? Sensing the battery. We'll go back again to page number 13 and CSI in and CSI P, that is the output current. Like we had please wait for a minute. We had CSSP and CSSN for the input side. Similarly, we have output CC. We have a CSIN and CSIP. You can see in a schematic diagram. This is CSIN. You see CSIN, and this is CSIP. Whereas this is CSSP and CSSN, basically for sensing the input current, and this is for sensing the output current across this register. Okay, how much current it is generating at the output. Okay, and this current will be proportional to the ICTL. You can see basically in the data sheet, and we'll go back to page number 16 to see the internal working and how they are connected. You see CSSP, CSSN is input side, right, and it's generating IINP, that is output for the input current monitor to the IO controller, and ICTL is input for setting the maximum current. Okay, this ICTL is again going to the charge logic. Okay, this is going to the charge logic, as well as this is going to the LVC, which is generating an output to the DC-DC converter. So how they are connecting this ICTL and CSIP and CSIN. You see over here this level shifter and this ICTL, they are connected. This ICTL is an output from the IO controller. It determines the maximum charging current, okay? And this CSIP and CSIN is connections from the register. From here, you see, from this register, from this register, and this CSIP and CSIN is going to a level shifter, and they are both determining to LVC. This LVC will match the value of ICTL with CSIP and CSIN, and it will generate a signal to the DC converter. If the current is less, it will give a signal to the internal DC converter to basically to change the timing of this gate signal, and so that more output current would be generated, which would be equal to the ICTL. So in that way, the IO controller controls the maximum charging current, because this CSIP, CSIN are connections from these registers, okay, and this ICTL is coming from IO controller, and both of them are going to an op-amp. This LVC matches this CSIP, CSIN and ICTL, and it automatically gives a signal to the internal DC-DC converter to generate DHI and DLO. They change the timing of DHI and DLO to generate more or less charging current, okay? Well, let's go back to page number 13, and this is basically DLO, DLOV and DHIV and SRC. We'll just go back to 16. You see over here what is basically an SRC. SRC is the top connection of inside driver for generating PDS, okay? PDS and PDL. Where is PDS? PDL. PDL is the output, the gate output to control this switch, and PDS is gate output to control this switch. You can also we can also tell it as PDS. To remember PDS, we can write it as pull down source, and PDL as pull down load, okay? Pull down source and pull down load. So here this SRC is basically a connection for the inside driver to generate PDS and PDL, and this PDS PDL is determined by the voltage difference over here. There is a switch logic. How does the maxim charger get to know that I have to turn this switch off or turn this switch off? Suppose, let's consider the case that adapter is present over here, okay? If an adapter is present over here, this is a P channel MOSFET, okay? So in that, if adapter is present over here, we'll consider the case. Let's go to the over here, yeah, AC adapter detection and power source connection. You can see when the adapter is present, the open drain AC OK output becomes high impedance. As I said, if adapter is present, then this AC OK will become high. This AC OK will become high, okay? This AC OK will become high, okay? And you see over here, the use a resistive voltage divider from the adapter output to the AC pin to set. When charging, the battery is isolated from the system load with the P channel PDL switch which is biased off, or you can see over here the positive bias input for the drivers connect to the SRC pin, and the negative bias connect to with this input the drivers can switch from SR to approximately 10 volts below. So we'll just, okay, so we'll now get to understand how this PDL and this PDS operates, okay? Let's go to again page number 13, and you see in page number 13 what exactly is PDS and PDL is. PDS is power source PMOS switch driver output, When maxim 1909 are powered down, the PDS output is pulled to SRC. Okay, let's understand this case. Let's suppose the adapter is present over here. Okay, this is a P channel MOSFET, but here the input is connected to the drain, so it will act as like a diode, and this voltage will go across this, right? So what's it's written over here in this, in the data sheet? When they are powered down, right? When they are powered down, let's suppose the case that adapter is not present over here. Okay, then if adapter is not present over here, then we have to turn this switch off, otherwise the DC back out will flow across this. So what it will do is, in that case, the PDS will drive the output at gate equal to SRC. You can see in the data sets clearly written, when maxim 190872 are powered down means if adapter is not present, the charger IC is powered down. It has no longer to generate a charging voltage or charging current. It's already powered down. In that case, the PDS output is pulled to SRC. Okay, it's pulled to SRC. So you can see SRC is connected to AD, that is adapter voltage. So in that case, the PDS value would be pulled to SRC. And how it does internally, we have to see in data sheet. So let's go to 16 number, and you see over here this PDS value would be pulled to SRC. When maxim charge is power down, that means there is no adapter present, then the PDS value would become SRC. In that case, what would happen? If this PDS, if gate becomes value of SRC, that is adapter, then this VGS is equal to 0. So VGS equal to 0, that means this MOSFET will turn off. No current will flow across this. This DC bat out will not flow across this, because we know in a P channel MOSFET, when input is connected here, if adapter is not present, DC bat out is present, here it acts like an input. Input is at source. To flow the current from source to drain, VGS has to be negative. But here, in that case, the PDS is pulled to SRC. And how does the charger IC know that? Charger IC know that no adapter is present. And how does it generate PDS and PDL? We can see here in data sheet. You see this PDS or PDL is coming from a switch logic, and this switch logic is controlled by a operational amplifier, by a op-amp, or by a comparator, which compares the voltages between DC in and battery. So if there is no adapter present over here, then this would give a less value, 0 value, that will disable this switch logic, and in that case the PDS would be turned to SRC, right? PDS would be turned to SRC. So if PDS is turned to SRC, and this voltage at gate would become voltage at source, so this would be turned off. And in this case, PDL, what is told about PDL? Let's see in data sheet. Everything is written in data sheet, and if we study it minutely, we can understand that IC very effectively. Okay, what is written about PDL? System load PMOS switch driver output, when maxim 19098725 powered on, the PDL output is pulled to ground. PDL output is pulled to ground. Let's see over here. PDL output is pulled to ground. So if adapter is not present, if suppose adapter was present, in that case if adapter is not present, what it's written, you can see in schematic once again. Let's see what it's written. The PDL output is pulled to ground. Okay, pulled to ground. So we'll see If it's pulled to ground, this is also P channel MOSFET. As I say, if input is connected to the source, then it would move through source to drain, only VGS is negative. But here, if adapter is not present, input is connected to the battery side, okay, so it will treat it like a like a diode and the current would flow. But if adapter is connected, then in that case this MOSFET would have turned off, because VG, this gate voltage, would be high at that time. If you check with multimeter, when adapter is present over here, then the value at this gate would be high, and in that case VGS would be 0. So this MOSFET will turn off, no current will go across this. Similarly, when you have removed the adapter and battery is present over here, this gate value would be low and it will drive current over here. So it's very important. And how it is generating this PDS and PDL? It's getting through its internal logic. Okay, over here, by checking the value between BAT and DC in, it is generating a signal to the switch logic. Okay, so now I think we have understood all the points. As I said, in charger IC, there are two important inputs. You can see over here. What are those? Those are ICTL, right? ICTL and VCTL. ICTL. So we have already spoken what is ICTL. We'll again revise. What is ICTL? ICTL is input for setting maximum output current. Maximum output current, right? We'll go back 16, and this is ICTL. This is coming from IO controller, and this is CSIP, CSIN. You can see in a schematic diagram what is CSIP. CSIP is this positive side, this is negative side. It is sensing the output current, and the input current, the ICTL, is the value given by the IO controller, and CSIP and CSI is the value that he actually sends. It is going to a level register. It will measure the value according to the ICTL. It will generate a signal to this to generate to control the timing of DHI and DLO, which is going to the gate of the MOSFET, external MOSFET, not internal. These are external MOSFET. Okay, DHI and DLO is generated through internal op-amp. You can see over here, it is generated through internal op-amp. DHI and DLA generated through the internal op-amp. Okay, so this ICTL is an input from the IO controller, and this Maxim charger generates two output. What are those two output? One is ACOK, which is a digital signal to the IO controller, which show the presence of adapter, and IINP, which is the input current sense monitor. And you can see IINP over here, how it is connected. IINP, you see IINP, the input is connected. CSSP and CSSN, you can see in a schematic. CSSP is connected to the input side. So these are a very important concept that we have studied over here, and we'll correlate this concept what we have studied to analyze the problems like battery not working, adapter plug-in but battery not charging. This will consider all this problem if we understand this signal PDS, PDL, and PDS and PDL is very important. ACOK is very important. DHI and DLO is very important. If DHI, DLO is not coming, what could be the scenario? Why it could not be coming? DHI and DLO. DHI is generated from an internal op-amp, and this is generated from a DC to DC converter. Seeing the block diagram, we can say this charger IC has very important component. One is charge logic, switch logic, and a DC to DC converter. So DHI and DLO is generated by this internal DC to DC converter, which is enabled by charge logic, and LVC. Okay, so if DHI is not generated, either this DC to DC, internal DC to DC converter is faulty, or this charge logic is faulty, or if charge logic is okay, it might have been given PK press signal, the battery may be faulty, the battery temperature would be high, and this would have pulled PK press high, and this will disable charging logic. It disable charging logic, that means no DHI and no DLO is present. So if we are checking such scenario, I will always advise to first remove a battery and try a new battery, and we'll use this concept to discuss the practical cases like battery working, adapter not charging, adapter charging, battery adapter okay, battery not charging, plugged in not charging. All cases can be solved if we understand these important signals. Okay, understanding this important signal is very important. So in the next class I will be covering the section after this, and I will be covering IO controller and ACPI. I'll first have a theoretical class on ACPI, and then I would cover the important aspects of IO controller, because IO controller is at the center of power management. Okay, and I'll cover another scheme, another data sheet, that is ISL 88731, which is very similar to this, because the board which we are referring, Lenovo Y570 or 470, is having ISL 88731. So let's open the 88731 data sheet. Okay, so now we'll study the data sheet of ISL 88731A, which is present as a charger IC in Lenovo Y570 and 470. We are referring two kind of board. One is DV2000 and another is Lenovo Y570 or 470. So let's understand what are the similarities between these two charger IC and what are the differences between these two charger IC. Okay, similar to the Maxim 8725, the important pins are DC in, AC in. Okay, like we see over here, DC in, and after DC in, it's an input to internal linear regulator. Similarly, it's an input to internal linear regulator which generates a voltage VDDP. Similarly, over here it generates LDO. Okay, so both of them are quite similar. And AC in, after it get AC in, it will generate AC OK. If adapter is present, this AC OK would be high value. If adapter is not present, AC OK would be less value. Similarly, we discussed in Maxim 8725. Okay, so these are DC in, AC in, AC OK. Now we have to check what are the inputs what are the inputs, output from this, main outputs from this Maxim charger IC. One is the AC OK and another is ICM, input current, that is input current monitor. Similarly over here as IINP. You see IINP generated by CSSP and CSSN. Similarly here in ISL 88731, this ICM is generated by CSSP and CSSN. We can see over here CSSP and CSSN. These are the inputs. These are connected to the input side. Okay, these are connected to the input side, CSSP and CSSN. And let's check over here. So these are the two important outputs of this charger IC. One is ACOK and ICM. Where they are going, we can see where they are going. This is ICM is going to host and ACOK is going to host. That is, it is going to the IO controller, AC in and DC in, CSSP and CSSN, and across this register we have CSOP and CSON, and in this Maxim 1909 we can see these are CSIP and CSIN. We can see over here in CSI, this is DV2000, CSIP and CSIP and CSIN, and here in Lenovo this is CSOP and CSOP and CSON. So it looks very much similar, right? It looks almost similar. and we have but one very important thing over here is there is no PDL, there is no PDS, there is no pull down load, no pull down source over here. That is, this portion is missing. This portion is missing from the ISL 88731. The question arises, why it's missing? It's missing because in Lenovo Y570 we said ACOK determines the origin of V in by adapter. Okay, we see over here this ACOK generated. If ACOK is not generated, then this switch will be open and this battery would be providing current to here to generate V in. But if ACOK is present, this switch is turned off, as we have discussed in the slide. In the slide we have already discussed this. You see over here, in the slide we have discussed, yes, ACOK is conducting, this is turned off, V in is generated. If no adapter present, this will not turn off and the battery section will provide V in. Whereas in DV2000 we have no such arrangement. We have a MOSFETs over here. Okay, we have MOSFETs over here. So we require PDL and PDS. Whereas this ISL 8873 is so smart, is very smart, is just doing the job with ACOK. Less connection inside this charger IC. And there is one more difference. There is SDA and SCL. That is SM bus connection from charger IC to the IO controller. Whereas in this one we don't have. You see over here, we don't have SMBC and SMBD connection. We don't have SM bus connection between the charger IC and the IO controller. There is an output. You see, there is an output. You can see there is an output from IO controller. What is the output? The output is ICTL. You can see over here there is no ICTL. So what was ICTL? That was the input for the output current, input limit for the output current. So where that value is now, how the IO controller is giving that value? The IO controller is giving that value through SDA and SCL, because this ISL 88731 is a very smart, very smarter than Maxim 8725. Inside this charger IC there are two resistors. One is charge current resistor and charge voltage resistor, and it's get its value from IO controller. So it is doing through communication. It's not hardwired. Whereas in DV2000 you can see this is ICTL. You can see ICTL Max 1909 ICTL, and you see this is hardwired with charger on functionality from IO. So there are two differences. One is there is no PDS PDL, it is doing the job with ACOK. There is no ICTL connection, no hardware connection, it is through SM bus. So it's a much smarter. We can say it's a more smarter than Maxim 8725, because there are two registers, charge current registers and charge voltage registers. You can see in the data sheet. If you go down, you can see there is an SM bus. It will look like you see over here. They have described about SM bus. We'll have a separate class on SM bus. No need to go into this detail right now. This class is already too much lengthy. So we'll have a different class, and we can sniff out data from this SM bus. So in the next class I would have just 30 minutes of class, and in that class I describe out SM bus and how to sniff out those data, because now the charger IC are getting more intelligent. They now have a direct SM bus connection from the IO IC, whereas in the previous version of the charger IC like Max 87825, they were hardwired. Okay, so I'll finish this class, and in the next class, just a small 30 minutes, I'll discuss about SM bus and sniffing out data from the SM bus, and after that we'll cover the IO controller. Thank you, and I request everybody to revise my videos again and again to understand the entire sequence. Okay, thank you.